Thank you. It is my pleasure to introduce the PhD defense of Mr. Tommaso Albrigi. Tommaso did his PhD here, which he will defend today under the supervision of Ricardo Rurali and Javier Rodriguez as a tutor from the UAB. First, I would like to introduce the members of the jury. We have an external reviewer, Claudia Fasolato, and a professor from here, from the UAB, Albert Beardo, and myself, Sebastián Reparaz, who I do work here. If you don't mind, would you like to introduce yourself?
Good morning. It's nice to be here. I'm Claudia Fasolato from Sapienza University of Rome. We'll bring an experimentalist point of view to the committee.
Good morning. I am Albert Beardo. I am an assistant professor here in the Department of Physics, and I do mostly theory. I like to model experiments as well, but my main expertise is on the Boltzmann transport equation and molecular dynamics.
Okay, then. So basically, the structure of the presentation will be, you will have something like maximum of 50 minutes of presentation. And after this, you will have some questions from us. Nice questions, of course, I hope. And after that, we will discuss the presentation and we'll call you back for giving you a final mark. Okay?
Okay. So thank you very much. Good morning, everybody. Good morning to the members of the commission and good morning, guests. And welcome to my thesis defense, which is about nanoscale phonon transport across semiconductor interfaces. In order to start, I want to share with you a curiosity. Okay, this is supposed to switch to the different slide. It's like not switching actually. Okay. Okay. So on the first slide, you can see the two most important symbols of the Christian and Hindu religion, respectively. And from these two religions, we can derive two quotes. The first one is from the Bible, the Genesis book, and is, "And God said, let there be light," putting sound before light and vision. In the second case, you can see the Ohm symbol, which represents the foresound, the sound from which the whole universe started, according to the Hindu religion. The first quote is attributed to Moses, and the second one to the Vedas, the Hindu holy scripture, and the two of them date back around the 15th century before Christ, which roughly corresponds to the late Bronze Age. Then, 4,500 years later, the guy in the picture, the most famous physicist ever, Albert Einstein, provided us with the theory of general relativity, according to which the universe started about 13.8 billion years ago with a big bang, and it became transparent only about 400,000 years after the Big Bang at the recombination epochs. So, 4,500 years later, we know that both Moses and the Vedas were right. Sound was there way before light. How did they know? In this thesis, I will start from an introduction, to giving you an introduction about phonons and the whole phononic spectrum. Then I will move to single interface thermal transport, where the case study will be given by the gallium arsenide germanium heterojunction. Then I will move to multiple interface thermal transport, where the case study will be given by the silicon germanium superlattice nanowire. And in the end, I will share with you some facts about Raman spectroscopy, where this case study is of superlattices, of course, where the case study is provided by the gallium arsenide, gallium phosphide superlattice, and the indium arsenide quinine superlattice. So the phonon is the elementary particle carrying sound, and it represents the quantized vibration of the atomic lattice or a material in general. Phonons can exist to a very broad, theoretically infinite, broad range of frequencies. Here I showed you a plot in a log scale where you can appreciate some of the applications that phonons found nowadays across various technological applications. And in particular, in this thesis covers just a tiny fraction of what is contained in the blue and violet boxes. So, thermal transport started with the guy in the picture, Joseph Fourier, around 200 years ago, and he asked himself what would have happened if he applied a hot and a cold temperature at the ends of any piece of homogeneous material and wait long enough for the system to reach a stable or steady state. In this case, he could already observe a linear decrease in temperature from the hot to the cold side and a stable heat flux across the material. From this very simple setup, he derived his laws, which basically states that the heat flux is proportional to the overall thermal gradient applied to the material times a constant, which incidentally defines the thermal conductivity of the given material. Now, what happens if we study a material which is non-homogeneous, but has, for example, an interface in between, like the one depicted there? Well, if you take a material like this one, a generic one, and we keep the two ends at fixed temperature, say TA and TB, with TA greater than TB, and wait for the system long enough to reach a steady state, the temperature profile will be different from the previous case. It will exhibit a pretty sharp temperature drop in the interface region. And this is an interfacial phenomena, meaning that interfaces introduce an extra thermal resistance, which is not captured in bulk theories. This is largely due to the fact that some phonons, when they reach the interface, when they were traveling from left to right, scatter on the interface. So the temperature on the two sides of the interface is appreciably different, especially at the nanoscale. The most straightforward way of characterizing this phenomenon is by introducing the so-called thermal boundary resistance, which is given by the ratio between the temperature drop at the interface and the heat flux, the steady-state heat flux across the material. Now, there are several possible means of studying thermal transport, theoretically, inside a given material. The first one is given by continuum theories. In this case, the material is treated as a continuum, as the name suggests. One actually solves or looks for the solution to the wave equation, which is a linear, in general, partial differential equation. And the solution is basically completely determined by the boundary condition one sets at the boundary of its material. A second means of describing thermal transport is provided by lattice dynamics. In this case, we are treating atoms as individual entities, and we are looking, or actually this is pretty easy, namely easy, we chase the analytical solution to the equation of motion of the harmonic lattice, and then we treat the interactions between the atoms, or the phonons, or whatsoever the elementary degrees of freedom we want to use, perturbatively. This has a very good side, which means that we can switch on and off the different orders in perturbation theory, meaning that we can, for example, switch off 3 phonon processes and only allow 4 phonon processes to take place, or do the converse, or whatsoever. But this is a finite order theory, meaning that we are not describing interactions at every order. Then the last means of describing thermal transport, in our case, is provided by molecular dynamics. In this case, one chases the numerical solution to the equation of motion for the ions and solves them numerically. This is a very good means of describing thermal transport as well, because it allows us a very direct comparison with the experiment, meaning that we are concretely just realizing in our simulation what we would do in the lab. But it has a counterpart somehow, that is, it is completely convoluted. I mean, this approach is non-perturbative, so it includes all order in perturbation theory, and we cannot switch on and off specific processes according to our will. And this is the means that we have chosen to carry on our study, thanks to its simplicity and direct comparison with the experiments. The case study is provided by the gallium arsenide germanium heterojunction. Here I give you a snippet of it. Why gallium arsenide germanium? Well, both of them are semiconductor material, meaning that the phonon is the principal heat carrier inside of them. The second reason is that it has a great technological interest. This junction can be found in high performance and high energy transistors and high efficiency solar cells, and they are lattice matched material, meaning that this junction can actually exist in nature, let's say at room temperature, without external constraints forcing the junction to exist. This is not a metastable state or something. This exists, actually. In order to describe it, we adopted a Thirlsdorf potential, which is a phenomenological potential that we can build using the parameters from both gallium and germanium. So we had a direct mean of describing the junction as well. To describe this system, well, we did the following. We took the junction, we thermostated the two ends at different temperatures, and we tracked the injected and extracted energy at the two ends. From the energy difference between the injected and extracted energy at the two ends, we could assess if the system had reached the steady state. Here you can see that there is a pretty clear steady state window, meaning that no additional energy is injected or removed from the system as a whole. We could select a steady state window, which goes roughly from 2 nanoseconds up to 7 nanometers, up to 7 nanoseconds. And within this steady state window, we averaged the instantaneous temperature of the ions, and we derived the steady state temperature profile of the junction, which is depicted in the plot there. From it, we performed a linear fit on the left and on the right of the interface. We projected the two lines on the interface, and from this, we extracted the temperature drop at the interface. Then, from the slopes of the injected or extracted energy, they're basically the same, in the steady state window, we could derive the heat flux across the junction, and from this we could derive, from the definition, the TBR by taking the ratio between the temperature drop and the heat flux. We performed a total of 42 simulations to study the geometrical dependency of the TBR on the specific junction we were simulating. In particular, 21 simulations were performed at fixed temperature bias, meaning that TA was 350 Kelvin and TB was 250 Kelvin. And 21 more simulations were performed at fixed temperature gradient, meaning that the interface temperature was kept fixed around 300 Kelvin, but we increased TA and decreased TB in order to keep a constant temperature gradient across the system. In both cases, we can see that 8 nanometers squared cross-section was already enough to achieve a pretty fair degree of accuracy and convergence in our simulation. And from the two plots, you can also see that 180 nanometers was already providing us with a pretty fair degree of accuracy in order to claim that our simulations were related to the infinitely extended system. So we picked this geometry and we moved on studying the dependency of the TBR on other quantities like the interface temperature and possible defects that can be found in nature, like, for example, chemical mixing. So, interface temperature, as the name says, corresponds to varying the interface temperature of the junction. So we apply a parallel shift to TA and TB up or down, and we repeat the whole simulation, and we see how the TBR depends on the interface temperature of the junction. We also did the simulations for 2 different junction lengths because we wanted to make sure that our simulation and our results did not really depend on the junction length, and the results confirmed that we already had achieved convergence at 180 nanometers. And the interesting fact is that from our simulations, we derived dependency of the TBR on the temperature interface, which goes like temperature to the power -1. In contrast with the simplest phenomenological model, which can be found in literature, these are semi-analytical model, which predict basically a dependency which would go like temperature to the power -3, which basically comes from the bylaw of specific heat. Here you can see a snippet of the chemically mixed junction for different mixing length. With mixing length, I refer to the length of the region where chemical mixing takes place. In order to do this, we perform the random substitution of gallium arsenide atoms, with germanium atoms, and we also did this with 3 different concentration decay kinds. In particular, the linear decay of the concentration, the soft exponential decay of the concentration, and the hard exponential decay of the concentration. Still, in the 3 cases, then we repeated the simulations for still something like 20 more simulations, and for the 3 decay kinds. And you can observe that there is a rather linear increase in the thermal boundary resistance with respect to the linear, to the mixing length, regardless of the specific the concentration decay, which was rather interesting because we would have expected that somehow the difference in the concentration decay would have affected the dependency, but no way. The mixing length is the only parameter affecting the TBR at this level. Then we moved forward and we studied how interface roughness affects the thermal boundary resistance of the junction. Here you can see a snippet of the interface of the junction with interface roughness. I also applied a minor vertical displacement to germanium atom in order to help you better visualize the rough interface. To do this, we basically generated random surfaces, different random surfaces with different values of the root mean square, 3 to be specific, and we computed the thermal boundary resistance for each one of these cases. And we could not observe any specific trend of the thermal boundary resistance with respect to the root mean square of the random surface we generated. Here with the 2 seeds, I am talking about 2 just a random starting point to generate the whole configuration. Then we studied rectification. Rectification has to do with the fact that since the system is non-homogeneous, when we swap the 2 temperatures, we will observe in general a thermal conductivity and a thermal boundary resistance which is not the same. Here you can see the temperature profiles in the forward and reverse configuration, where you can appreciate that even if the conditions at the ends of the junctions are perfectly symmetrical, the temperature profile is not symmetrical with respect to the interface zone. And what we did is compute the the rectification coefficient is basically given by the % difference in thermal conductivity in the forward and reverse conditions. We computed these thermal conductivities, so we could extract the rectification coefficient for different junction lengths. Why? Because the longer the junction becomes, the less the thermal boundary resistance affects the rectification coefficient, which becomes solely determined by the difference in thermal conductivities between gallium arsenide and germanium. In this case, we plotted the inverse thermal conductivity with respect to the inverse junction length, which allowed, and then we performed a linear fit, and this allowed us to extract the thermal conductivity of the junction in the forward and reverse condition at infinite length, which it corresponds to length to the -1 going to 0. And from this, we observed a thermal rectification coefficient of around 30%, which is a pretty fair value, and that could allow some applications, some technological applications. And the results of all this study about the gallium arsenide germanium heterojunctions have been published on a paper in Applied Physics Letter that we published that Applied Physics Letter published in 2024. Then, after the single interface thermal transport, we started studying multiple interface thermal transport, where the case study was provided by the silicon germanium superlattice. Here you can see a snippet of the silicon germanium superlattice nanowire. A superlattice is basically a periodic arrangement of different materials at the nanoscale. Here I need to stress what a phonon is in this case. A phonon is a quasi-particle, meaning that it is an elementary excitation of the atomic lattice which possess particle-like properties like a definite position, velocity, and extension. Okay. Now, in a simple lattice like this one, with only one atom kind, you don't have any length to compare with the Phonon wavelength. But in a superlattice, the superlattice period introduces a scale. And this scale is exactly what allows us to talk about short and long wavelength phonon. Now, if you look at this, it is pretty clear that a long wavelength phonon, so an excitation like the bottom one, will experience just a sort of average material with average properties and will be completely insensible with the interface structure. Whereas an excitation like this one will experience a sequence of interfaces along its path. This has to do, and also these two different excitations would travel in a very different way inside of the material. This can be seen in the interface, in the temperature profile of the superlattice. If we repeat the study, so we apply a definite temperature bias, we wait for the reaching of a steady state, and we compute the steady state temperature profile, which is shown here. You can see that when the mean free path of the phonon, so the distance the phonon travels, is much longer than the superlattice period. Here the mean free path is stable and we change the period, but because we cannot really change the mean free path, we can change the superlattice period. When the superlattice period is much shorter than the mean free path of the phonon, the phonons basically experience a sort of continuous material with average properties. So the superlattice period does not appear in the temperature profile. But as we make the superlattice period longer and longer, the mean free path of the phonons becomes shorter and shorter in comparison to this superlattice period, and the superlattice structure appears in the temperature profile, in the steady state temperature profile, signaling a transition from the coherent to the diffusive regimes of the phonons within the superlattice. If we compute the thermal conductivity with respect to the superlattice period, we'll observe that in fact, at very short superlattice period, the thermal conductivity is rather high, meaning that the phonons are experiencing an average material and they're just propagating through it without experiencing a series of interfaces. Then the same happens for very long periods, meaning that when we are at very long periods, the phonons will experience a sequence of interfaces and the thermal conductivity will scale linearly with the inverse interface density. In between, there is a minimum in the thermal conductivity, which corresponds to the transition zone between the coherent and diffusive transport regimes for the phonons. And it is very interesting that this transition has been observed in the experiment as well, and it's going to be published, hopefully soon, in a paper which we are working on with Zardo's group in Basel and Sorba's group from Pisa. So this has been observed in the experiment and also in our simulation, so we are happy with that. Now, for the silicon germanium superlattice, a very interesting fact is that it provides us with two different interface kind, depending to a slight shift that we can apply when we tailor the superlattice on the blank underlying lattice. Here, if you zoom on the interface region, you can appreciate that the coupling between silicon and germanium atoms is different in the two configurations. And this yields a different thermal boundary resistance in the two cases, which then yields a different thermal conductivity for the two cases. And you can really appreciate that there is sort of like a rigid shift between the thermal conductivity as a function of the superlattice period for the tight, I call them tight and loose just because here it looks tight and here it looks loose, interfaces. Plus, we also asked ourselves what would have happened if we just used a period to tailor a superlattice period, which was not an exact multiple of the underlying blank period, of the underlying lattice period. And in this case, the interfaces change in a sort of random fashion, when we move along the superlattice. In this case, it is very interesting that the minimum does not appear. So there is a sort of no coherent regime for this sort of free superlattices. But this lack of a minima is not observed in the experiment. it is rather unreasonable to expect that we have this degree of control in the experiment on the specific interface, but this is not observed, and we could not really assess why by means of our simulation. Now, we also studied the bulk case, meaning no superlattice nanowire for the silicon germanium, and in this case we performed 3 different geometrical configurations where we could still observe clearly a transition from the coherent to the diffusive regimes, and of course a slightly higher thermal conductivity for the greater number of phonons present in the 180 nanometers long superlattice. And then we adopted a slightly more sophisticated technique to simulate thermal transport across the silicon germanium superlattice, which does not rely on phenomenological potential, but rather on quantities that can be derived sort of directly from quantum mechanics. This goes under the name of BTE, which is the transport. Basically, you can imagine that it's just a transport equation for the phonons inside the superlattice, and we choose also a specific approximation because the simulations were resulting the same. And we computed the thermal conductivity of the bulk silicon germanium superlattice at different temperature and for different superlattice periods along the two different crystal direction, in particular 111 and 100. And you can see that in the two cases, there is always a clear minimum in the thermal conductivity, except for the 100 crystal direction at 100 Kelvin, where we also repeated the simulation batch, avoiding the approximation, but still no minimum appeared, and we assumed that this must result from some probably quantum effect, which become dominant at low temperature, which are not captured still by our formalism. We also repeated this simulation with not rough, but chemically mixed interfaces for the two crystal direction, 111 and 100, and you can appreciate that the introduction of a slight chemical mixing really sharpens the decay of the thermal conductivity when we move from the coherent to the diffusive regime, and also enhances the linear dependency of the thermal conductivity with respect to the superlattice period when we move to longer and longer period. So after said all of this, this concludes basically our study of the thermal transport across the single interface and multiple interface cases, and we can spend some time talking about Raman spectroscopy. In order to talk about Raman spectroscopy, well, I need to say that in order to deal with this computationally, you need to include quantum mechanics and include the electrons into your simulations. To do so, we use density functional theory, which is a means of describing the electrons in a computationally efficient fashion. When we are in this setup, we can say that phonons, well, this happens whenever you have an atomic lattice where the primitive cell contains more than a single atom. The phonon spectrum is not continuously increasing from 0 up to some higher energy, but there are some phonons which possess a definite 0-point energy different from 0, meaning that you cannot excite these excitations, these phonons, with an arbitrary low amount of energy. This opens the way to, well, here I depicted a very simple setup, a very simple experimental setup for a Raman spectroscopy, where you shine some laser light on your sample, and then you collect the scattered light at the detector. Since some phonons have a definite non-zero point energy, you can observe an energy shift. And well, there are three main cases. You can observe no shift in the scattered light, an energy loss, meaning that some light has been absorbed by the sample, and an energy gain, meaning that some light has been released by the sample to the detector. This shift in frequency, this provides you with a shift in frequency with respect between the incident and the scattered light, which goes under the Raman shift, which is what you plot when you want to compute when you want to measure the Raman spectra of the material. We computed the Raman spectra of the gallium arsenide gallium phosphide superlattice for 5 different superlattice periods. Here I show you the shortest period we simulated, which is basically the shortest possible superlattice period, and the mid-well with 3 repetitions of gallium phosphide and 3 repetitions of gallium arsenide. In order, since this is a quantum mechanical study, we had to perform some more sophisticated convergence study. The first of them has to do with the number of K points we used the number of points we used to sample the Brillouin zone, which is the zone of the different non-equivalent crystal directions where the phonons can propagate, and also with respect to the energy cutoff we use for the plane wave basis to perform our study. Here you can see in the plot the relative phonon frequency with respect to their value at the highest resolution we could simulate, both as a function of the number of K points and as a function of the energy cutoff. And you can appreciate that we already reached a very fair degree of accuracy at 8 K points to describe the Brillouin zone and the 37 Hartree as the energy cutoff for the plane wave basis. So we adopted these convergence setup, this setup for our further simulation, and we computed the Raman spectra of the gallium arsenide, gallium phosphide superlattice. Here, well, these superlattices, we studied these superlattices also because they have been grown in the experiments. Here you can appreciate a real picture of some gallium arsenide, gallium phosphide, gallium arsenide superlattice nanowires grown in the lab from these are pictures which have been taken in Basel, and these nanowires have been grown in Pisa from 2 groups we've been working with. So we computed the Raman spectra of this superlattice for the 5 period I mentioned before, and you can appreciate here the results of the Raman spectra for the shortest, mid, and longest period we have simulated. The situation is particularly interesting. You can see that in every plot, the 2 optical frequencies of both gallium phosphide and gallium arsenide are clearly present and shape the overall structure of the Raman spectra. Then the modification of the superlattice period, so introducing more and more atoms in the primitive cell of the superlattice, introduces more peaks. Well, it also slightly shifts the principal peaks from their position, but it introduces more optical frequencies. You can really see that the more the period gets longer, the more you get peaks and peaks, meaning different phonon modes and optical frequencies. And this is particularly interesting because it makes clear, it is the proof that superlattices can be used as a viable means of engineering the phonon spectra of the material, and then also to tune and control their optical and then thermal transport properties, because, as I said before, the phonons are the particle carrying energy in these structures. Apart from this class of superlattices, well, the results of this paper have been published. The results of this study, both experimental and computational, have been published in an applied physics, applied nanomaterial in 2023 in collaboration with Zardo's group from Basel and Sorba's group from Pisa. And apart from these superlattices, we also studied a special kind of superlattices which go under the name of twinning superlattices, where the superlattice structure is not provided by chemical switching between atoms of different species, but from the mirror imaging of the primitive cell of the superlattice with itself. So you can really appreciate this sort of transition between 2 different geometrical, I would say, geometrical or chiral configuration of the very same material. And in this case, interestingly enough, well, we could simulate up to 6.3 nanometers. These computations are particularly heavy. And we computed the Raman spectra of these 3 superlattices. Here I show you the shortest, well, the Raman spectra of the shortest one and of the longest one. And you can see, you can appreciate it, you can appreciate how, even in this case, the superposition, the imposition of a superlattice structure still works and affects the Raman spectra of the material. You can see in a completely evident fashion the principal peaks which correspond to the optical frequency of indium arsenide, and then you can see how modifying the superlattice period, so introducing longer and longer privative cells, leads to the appearance of new optical modes adorning basically the principal peaks of the indium arsenide material. And this is very interesting because it proves that also twinning superlattices can be used as a mean of engineering the phonon spectra and the optical properties and the thermal transport properties of a given material, not only the chemical ones. So, to recap, in this thesis, I worked with thermal transport across single interfaces, where the single interface is basically provided by heterojunctions. These heterojunctions are very interesting in the fact that they allow means of doing some temperature control. We can keep the temperature different at the two sides of the junction, and they also allow thermal rectification, which paves the way to several technological applications, including but not limited to phonon logic. Then we also described superlattices, which correspond to multiple interface structure. We have seen that in this case we can observe different phonon transport regimes, in particular the coherent phonon transport regimes, which was not available till superlattices was not observed until superlattices became available. We can observe the coherent phonon transport regime only in superlattices, and we have also seen how superlattices provide us a viable means of tuning the phonon spectra of the material and controlling and engineering the thermal transport and electro-optical properties of a given material, if you can use it, a given class or set of materials, as long as you can use them to arrange a superlattice. Some possible continuations of my study would have to do with the utilization of machine-learned potentials instead of the phenomenological potentials we have used to perform our studies. And it is reasonable to think that with a machine-learned potentials, which is not available for the time being, we could achieve a quantitative and not only descriptive modelization of the system I've showed you so far. Plus, it would be interesting to see if it is to extend the study we have performed to other materials and material classes, as long as the phonon is the principal heat carrier inside the material and superlattices or heterojunctions can be formed. And with this, I thank you very much for your attention.
Okay, thank you very much for a very nice presentation and for keeping us well within the time. So I would like to offer you to start, Claudia, if you don't mind, with some questions. Okay?
Sure.
You need to take water and take a minute, please. Go ahead.
Thank you very much. You could tell me I was dry.
Thank you for the presentation. So very first question that I would say arises quite naturally from reading your thesis. Can you motivate the material choice? Because it's not constant throughout the thesis.
Okay, well.
Maybe that's in relation with some realization or existing systems.
Well, do you want the answer to be more related to the heterojunction or to the superlattices or a general one?
Please.
Both. Okay, so I'm not sure how to exit the presentation. Maybe this works, yeah. About the heterojunction, I think that I spent a little time here, maybe I didn't stress the thing enough. The reason why we studied the gallium arsenide, the germanium heterojunction, well, the very first one is that both of them are semiconductor materials. So the phonon is the principal heat carrier, and they can be studied by means of molecular dynamics. The second reason, probably this should have been the first one, sorry for that, is that they are materials of great technological interest. You know better than me that germanium was the very first semiconductor used in electronics, and that silicon took place only afterwards for some reasons. But germanium is still the preferred choice for high power applications. And the gallium arsenide germanium heterojunction is interesting because it is basically an interface that is found in, I mean, it has a great technological interest. You can find it in high performance and high power transitions, and also in high efficiency solar cells. Plus, we wanted to study this class of materials, this heterojunction, because gallium arsenide and germanium basically have the very same lattice structure and the very same period. I mean, their period is essentially the same. So this junction can exist without the application of external constraints.
Yeah, I mean, this was kind of clear. Thank you. And what about moving to the next example where you had silicon and germanium?
Yeah.
So what about the realizability of that system?
Okay, well, it is possible to realize this system. The reason is the following. There is a slight lattice mismatch between silicon and germanium, but in nanowires, you can have this very nice phenomenon, which is that the longitudinal stress is released in the lateral expansion or compression, depending on the point of view, because one gets compressed and the other one gets expanded, of the two lattices. So this nanowire can exist in nature. So these silicon and germanium provide a viable means of realizing these materials in practice and in the experiments, and they can be used then for electronical applications and electro-optical applications, because they are both semiconductor materials, just like gallium arsenide and germanium. And the figure of merit, I would say, I mean, these superlattices allow very good tunability of the thermal conductivity. You can achieve a very low thermal conductivity, which then would increase the electrical efficiency of the nanowire in technological applications.
Okay, thank you. So I guess that also for the last part, you related to systems that exist. Well, you showed that.
Yeah, these are actually, yeah, definitely.
Okay, nice. So now we move to the Raman part, if you don't mind. So in slide 17,
sure,
you mentioned that there are some modes which dispersion goes to 0. So why are we interested in that part of the Brilliant Zone?
Yeah, I mean, the reason is that you want to observe if your phonons would have if they could make a smooth transition to the 0-point energy, you could excite them in a continuous fashion, and you wouldn't observe any finite drop in the energy of the shift. You would just shine some light and you would see that some phonons start moving, but it's just like electrical conductivity. So imagine this, you apply a definite voltage difference to a metal, to a conductor, and you will see a current which increases linearly with the applied voltage. In this case, you do not see any smooth transition, you don't see any smooth excitation, and this is what allows the system to store some energy inside of it. I mean, optical phonon can actually store some energy away from the 0 point, and they cannot release it without an external excitation or absorbing.
So I kind of agree with the second part. I'm doubtful about the first, like the way you describe the physics of Raman.
Yeah, maybe you should not do comparisons with the electrical.
I mean, so can we probe like any part of that red branch with the Raman spectroscopy experiment?
No, we can only, I mean, If we could maybe shine single photons into the sample, could be, but I would say that we are just proving the zero momentum zone of the spectrum, because we are exciting just the bulk material. So the phonons that we excite inside of the material are completely delocalized. We are just exciting the oscillations of the primitive cell, but there is no modulation of the specific phonon mode along the superlattice with the current technology. So we are probing.
It's kind of a more intrinsic limitation. Maybe we can discuss.
Intrinsic, yeah.
Like it depends on momentum conservation and the momentum that
okay.
deliver with the photons.
Yeah, of course.
I mean, you would need heavier particles to reach the edges of the brilliant zone. Okay, so then moving to the Raman spectra of the superlattices that you showed. Yeah, you mentioned that the frequencies of the phonons that appear in bulk materials. Can you point to me, please, the characteristic frequencies? I'm very bad with memory. So like
this one and this one.
Okay.
The principal peaks, this is basically a recurrent phenomenon. You have two materials involved in the creation of the superlattice, and they still possess their own optical frequencies. You can see them when you compute, when you measure the Raman spectra of the superlattice you have constructed using these two materials. They are still appearing pretty clearly. They represent the principal peaks of the spectra. And then you can observe that increasing the period shifts slightly these peaks. You can see that there is a very slight shift here, for example, in the red one, with toward the left, so it reduces the frequency. And but the most important, the most important part of this superlattice structure is that it actually creates new phonon modes in a number which is determined by the number of atoms in the primitive cell, and then also on the activity, on the optical activities of the phonon modes, because none of them are.
We will get there. So before I was wondering, since you didn't mention in the discussion, what about the three different colors and the...
Oh, yes, I was worried about it.
That's fine. I mean, just
for sure.
Why do we look at these?
Definitely. Well, when we perform a Raman scattering experiment, we are shining some laser light and then collecting some laser light, collecting the scattering light at the detector. Light carries a polarization, a definite polarization. So you will have an incident polarization and a scattered polarization. Here I plotted the three non-equivalent polarization setups because since our theories are symmetrical with respect to time reversal, if you take the YZ or ZY or whatever scattering configuration, scattering setup, you wouldn't see any difference. And I only plotted double Y, YZ, and double Z because the X and Y directions are equivalent in this superlattice because it's a Wurtz primitive cells, so the X and Y.
So, but why are there peaks that we can only see in the red and blue spectrum, and we cannot see them in the yellow spectrum, for example, and vice versa?
The reason is that not every phonon mode, so not any vibrational mode, is optically active. And this has to do with the different response function. When you compute the Raman tensors, you have to study how the system reacts to the incident light and to the variation of the incident light and to the variation of the electron cloud surrounding the nuclei. So some phonon modes, so some acoustic, it is wrong to call them acoustic, some phonon modes are not optically active and you cannot observe them.
So basically you're mapping the Raman tensors with those, right? Can you say that?
Not exactly the full Raman tensor, because you're
some parts of
it for sure.
And then in order to map the other parts of the Raman tensors, you would need some sort of rearrangement of the superlattice, right? Like
I guess I would need to show you the precise way in which, like transverse optical mode or longitudinal optic, I would need to show you the actual way the atoms get displaced and react to the incident light when you shine some laser on them. I would do something like that because it's a third order tensor, if I'm not wrong. Here you're not seeing it.
Yeah, okay. I think
if I answered correctly.
Yeah, I think that's enough on that. So I have one last question, if I might, and it's on something that you wrote on the thesis but didn't mention today. So just, I'm not sure I got it correctly, so I took some notes. So at a certain point, when you compare the response of the, let's say, compositional superlattice with the twin superlattice, you kind of link the strength of the Raman peaks to the homogeneity of the force field, and then you use this to, at least to my eyes of a reader, in support of the fact that twin boundaries are not that efficient phonon scatterers compared to compositional boundaries. So first I would like to ask, how do you link the strength of phonon peaks with the homogeneity of the force field? Because to my, let's say, as a first intuition, I would link it to some electronic responsivity rather than to the homogeneity of the force field, meaning it's not for granted that if you change the composition, the peaks increase in the intensity. And so I would like you to comment on that. And the second thing is, isn't it like intuitive that a twin boundary scatters phonons less than a compositional boundary, to your understanding? And
no way. I mean, if I can I will answer the question the opposite way. So second question, no way, meaning that nature is so rich that you cannot, maybe you can have an intuition, but nature is always ready to surprise you in a way you cannot expect. So in general, you cannot tell just that because you implemented a superlattice structure by means of twinning, you will observe a slighter modification of the optical spectrum of the material. This is not something that you can say in general. It's sort of naive to believe it. We observe it in practice also because I mean, in the two cases, you have two different masses, two different optical modes. So this allows, in principle, a greater degree of mixing, and you can expect that you will see a richer structure, whereas in the second case, no. But as long as you don't resolve the Hamiltonian and you compute the actual phonon frequencies, you cannot tell, because just because an Hamiltonian says just some minor term out of the diagonal, it doesn't mean that when you diagonalize it, the frequencies will be the...
You know, I would reason in another way, saying, okay, the material...
very theoretical point of view, sort of.
Yeah, like the material is the same, so you would expect it to behave bulk-like, and then maybe there is some difference, so it's really a different starting point. And what about the intensity of the Raman peaks?
The intensity of the Raman peaks, I guess that I sort of... cheated, meaning that we can only assess that in the afterwards. So only after having computed the spectrum, we observe that actually in the twinning superlattice case, the superlattice structure only affected the Raman spectra in a minor way. Because in principle, well, of course, you will expect a more homogeneous electronic density along the lattice, because basically electrons are facing the same amount of charge in the nuclei and stuff. But electrons are so strange and quantum and unpredictable that you can only assess what is going to happen once you have computed the full wave function, whatever the approximation you use, and you have computed the full electro-optical response of the system for the twinning superlattice. So I would say that the strength of the peak is something that somehow you could have expected it, but I would never personally, this is my personal opinion, I would never take it for granted just because someone tells me, hey, you know what, I'm just doing a minor modification on it. No, look, quantum mechanics takes something minuscule and makes it huge.
Yeah, sorry. Then one last comment. So it seems to me that you kind of understand the world from a theoretical point of view, but do we need the benchmarking for these calculations, or do we trust them like really?
Oh, I would sort of trust them because the theory behind this simulation is pretty well done. I mean, here we are really taking quantum mechanics into account to a very good degree of approximation. Of course, still you need to make some approximation. Physics is all about approximations. Everyone into the field knows this. You can never know if some relativistic effect would kick in. You can never know. But the ab initio software, which implements quantum mechanics and taking electron into account and their quantum nature. Okay, for example, you cannot predict superconductivity with this formalism, because superconductivity has to do with the wave function, with the phase of the wave function, and you're not keeping track of that here.
Yeah.
But it is enough to compute the electro-optical properties.
So my question was like, okay, so now I do an experiment, I measure the spectra, and they will be perfectly superimposable to the spectra you computed here, or not?
Not perfectly, for several reasons. For example, in these superlattices, you have, I mean, these are superlattice, we can perform the experiments on superlattice nanowires, whereas we can only compute the spectra of the bulk superlattice. We cannot simulate system as large as the one we have in the experiments. Plus, in order to exist, this nanowire, you can see the superlattice nanowire, it is enclosed into a gallium phosphide shell, and this is necessary, and also it has the bottom and the top of it is made of gallium arsenide, otherwise it cannot exist in nature. I mean, we know how to grow the superlattices, but only inside a sort of shell of gallium phosphide. So when we perform the experiments, there are many sources of minor modification to the spectra. I would assume that if you could really take a bulk superlattice in the experiments and perform with perfectly flat interfaces and everything, perfect periodicity and everything, and compute and measure the Raman spectra, it would match pretty well our predictions. This is not, of course, super perfect somehow. It does not include every possible effect. We will never get there, in my opinion. Not only about condensed matter physics. I mean, you always have something kicking in at some point. But I would assume that they would match pretty well. And indeed, we compared our simulations with the experiments in the paper I mentioned there. The problem with that is that the longest period that we could simulate was still slightly shorter than the shortest period that they could grow in the experiment. So there is some compatibility, there is some correspondence, we were happy with that, but you cannot just expect the two pictures to overlap and that's it.
Okay, I think that's fine for now.
Thank you. Thanks for the presentation and for the thesis. It's nice to see so many computational techniques to characterize phonons in a single thesis. I also appreciate the precision in describing the methods and the protocols. And also, I believe, in my opinion, your calculations are very robust, look very consistent. So I have two main questions about the physics and then some technical questions. First, one of the main, or in my opinion, most impressive result of the thesis is the rectification. You measured and you highlighted in your letter. So I think you achieved a 30% rectification in specific cases. So, well, there is a lot of debates if this is feasible.
Sorry, there is a lot of
debates going on if this is feasible in reality. And if I understand this correctly, there are two effects that might play a role to explain this rectification. One is the fact that the thermal conductivity of the two materials display a different temperature dependence, meaning that the conductivity when one side is hot might change differently than when you swap the temperature profile. And then there is the effect of the fact that the available vibrational states are different at different temperatures, so the acoustic mismatch might be different when the thermal temperature profile is reversed. So which of these two effects do you think that explains your rectification?
The first one, definitely the first one. Yeah, it is because, and that's exactly why we wanted to perform the convergence study for the infinite length, because the thermal boundary resistance affects the thermal conductivity only as long as you're working at a scale which makes that temperature drop comparable to the overall temperature drop. There is a quantity I haven't discussed in this presentation and not even in my thesis, which is called the Kapitsa length, which provides you a scale at which the thermal boundary resistance becomes completely, it becomes like not meaningless, but it doesn't really affect your neglectable. Thank you very much. Thank you very much. And so here what we wanted to do is to sort of remove the dependence of the rectification coefficient on the thermal boundary resistance, because in practice we are interested in junctions, in heterojunctions that are infinite compared to the nanoscale. So we will only see the rectification, the contribute to rectification coming from the different temperature dependence of the temperature of the conductivity on temperature of the two materials.
I see. Okay, then this is a nonlinear effect, meaning that if you increase the temperature difference, this effect will, the diodicity will be enhanced, so the rectification will be enhanced. Is that right?
It is a non-linear effect, of course.
In the sense that, of course, if like the temperature difference is very big,
then it will disappear. The rectification will definitely disappear.
So the conditions you simulated are close to a situation that we could expect in a nanoelectronic device. I mean, we are in the range of temperature differences that...
Yeah, I have to mention that we... I mean, here I performed this simulation at where the interface temperature was kept at 300 Kelvin. So probably in a real device, you would have some heating, it would heat up a bit, but I have shown a few slides before, and I would think that this is still meaningful, that temperature, we know how temperature affects our simulation, the contribution of thermal boundary resistance. So I would say that if you increase, I mean, these results are okay. We are actually simulating conditions that can be found in real life application and technologies according to the interface temperature. But I have to mention that the thermal gradients that we deal with in this simulation are completely not realistic. And this is just a computational compromise that we need to accept, because if we want, in order to perform this simulation, we have to use a pretty slow resolution of about, sorry, I want to show you this. Okay. Here I'm simulating 7 nanoseconds. To simulate 7 nanoseconds, I am resolving the equation of motion for 100,000 of ions with a resolution of 0.7 femtoseconds. So I am performing something like 10 million steps, 100,000 atoms. These are very heavy simulations. You need to run supercomputers for hours and hours and possibly days to get one single data point. And in order to achieve convergence, you need to get your system reach the steady state pretty quickly. In order to do this, we increase the temperature difference, because of course everyone has a pretty fair physical intuition of this. If I apply 1 Kelvin of temperature bias, it will take minutes, probably hours, to get to a steady state. So it's completely impossible to perform the simulation. I mean, it would have taken more than my whole PhD to perform just one data point. So we use these incredibly high temperature gradients, which are way higher than the temperature gradient that we have from the core of the sun to its surface. I mean, it's incredibly used. It's billions of kelvins per meters. It's impossible. I mean, not even in neutron stars you have those temperature gradients. That was a thing which...
that's very important, and I guess that's one of the main problems when it comes to compare with experiments. So, but then I understand that you expect that you will still observe this rectification with a much smaller thermal gradient. You would expect it?
I have to say that up to my knowledge, thermal rectification is still pretty elusive. I mean, it hasn't been observed in the experiment in like not a fair fashion, but like people claiming unanimously that there was a thermal rectification. And it is because it's always unclear if something is disturbing your measurements, if you're not really putting yourself in the proper experimental conditions, and so on. I would expect that in a few years people will observe thermal rectification, because I don't see a huge problem somehow with these simulations. They are pretty reliable, at least in the way they are descriptive. It's not a quantitative description of the system, because these are phenomenological potentials, but I mean, those are the interactions between the ions. You don't expect electron to do much here.
Okay. No, that's...
The ions are classical, so we are describing the system well. So if this appears in our simulations, we should be able, maybe when we will get to the nanoscale, a little bit better than now. And
okay.
Yeah.
Okay, no, I think that's enough. So I had another question about the other main result, which is the transition from coherence to a diffusive behavior. So it's very nice that you can correlate this linear temperature profile with the coherent regime. And in MD, in principle, you are modeling full physics simulations, in the sense that you have both incoherent mechanism and also coherent mechanism. So to me, it's very natural that you can observe this in MD. But when it comes to the BTE is a particle-like description of phonons, meaning that you are modeling the phonon gas distribution function. Definitely. So they are particles. They have a well-defined velocity that you can relate with the dispersion, but basically you have a group velocity and a scattering probability. So I was surprised to see that in the BTE you also recover a minima. Yeah. And my question is, what boundary conditions are you using to reproduce such a minima? Because I mean, you have an interface. You need to decide in the BTE if you are assuming inelastic scattering, elastic scattering, a probability to cross through the interface with no scattering, which would be the metamaterial picture. So how do you set the boundary conditions in the BTE to reproduce this minima?
Well, here, I'm not sure if I'm answering correctly, but in order to introduce the boundary resistance between different layers, BTE uses actually the acoustic mixed match model. It is implemented, so there is a sort of trick. It's not, you take a result from something which doesn't have much to do with the BTE, and you plug it into your BTE to compute your simulation. This is one part of the answer. The other part of the answer is that we put just periodic boundary condition across on the plane perpendicular to the transport direction, and of course no periodic boundary condition along the transport direction.
So this is basically the acoustic mismatch model is reproducing this minima. Okay. So then it comes, my next question is the following. So from your experience, is there any good mesoscopic model, acoustic mismatch model, diffusive mismatch model, to mesoscopically describe interfacial transport, or we need to rely on simulation? Because you compared AMM with your simulation, it's clearly off. You don't even compare with the MM, which is usually used at high temperature. So the conclusion is that these models are not capable of capturing the physics, or what's your feeling?
I know that, I mean, somehow no model could really capture the whole thing. It usually happens that a model works better in a specific condition, another model works better in another one. Of course, you would expect that the more refined the model is, the better it works, but often in physics it is a matter of finding the balance between the two. So up to my knowledge, it doesn't exist any general framework under which we can describe the full scenario. We really need to rely on several models and maybe to try to describe the system with one of them, the other one, and the other one, and then try to see which is the red line connecting the full thing.
Okay, so in this sense,
there is no mesoscopic, yeah, there is no one.
And then the BT is also tricky to use.
Yeah.
No. So also, I wonder if
it's exact. The BT is exact. It can be derived exactly from quantum field theory, but then you need to perform approximation still in order to use it and to simulate and to plug the interface, the thermal boundary resistance.
That's right. So we know that the BT works in the bulk. We can read it with DFT, and it predicts the bulk conductivity. But when it comes to boundary conditions,
exactly.
Also, I guess that when you simulate the nanowire, you also need boundary conditions for the free surfaces, right?
We just simulated, of course. When it comes to the nanowire, we haven't simulated the nanowire using BTE. Okay. BTE was only about the bulk. We only simulated the nanowire using molecular dynamics.
Okay,
and of course, here you don't have any boundary condition in the cross plane.
Okay. Nice. So then I also have some questions about the choices you did, which I guess is one of the most important or one important contribution of the thesis. No, I guess the decisions that you propose, the choices you did, is also what you propose that the people should use following your work. No, so you decided to use Tersov. I understand that it's because you have different species, and Tersov, it's easy to implement in this sense. No, there is no much assumptions going on. But I saw that you also use the velocity rescaling approach to model the thermostats, rather than, for example, a Langevin thermostat or a Nose-Hoover thermostat. So, and I was not able to see the motivation for this choice.
Okay, I haven't stressed that much in the thesis, but the reason is that this sort of thermostating technique that is here, let's say, introduces some biases away from the close to the thermostated zone. It's introduced some non-physical phenomenon because, of course, you don't get any velocity rescaling in the experiments. But it is very good because it allows energy conservation, and it is the preferred choice when you are not looking for like equilibrium properties. We are describing a system which is fundamentally out of equilibrium, and you could use some more sophisticated thermostating techniques, which then you couple the system to another system, a reservoir, and then you solve the full equation of motion, so energy is strictly conserved. You're not introducing any numerical modification to the solution of the equation of motion, but still that would have been completely meaningless in this case because you are only interested in the interface zone, because there is a result, I haven't mentioned it here, from probably Ricardo, which shows that the thermal boundary resistance is a property of the interface. It only depends on the interface. So as long as you can neglect what is going on far from the interface, you're fine with this. And this is why we have taken this. I mean, it's one of the most standard means of tackling the thing.
And with this method, you don't see any temperature jump in between the thermostat and the system. Here you show the profile within the free atoms.
I am sure, yeah, this is just a region close to the interface, of course.
You also have a TBR between the thermostat and the system as well?
Is not a TBR because you don't see, if you look at the, I mean, this is just, I'm just recollecting my memories. You don't see a sharp drop. You see a smooth, very pronounced drop, but it's a smooth one, and it's completely non-physical. And you cannot assume that it has to do with the different temperature that you have, because you know that the thermal conductivity varies not in a linear fashion, but sort of linear fashion with temperature. So you would observe a sort of asymmetrical situation near the cold and the hot thermostats, whereas the situation is heavily symmetrical. So it is clearly a computational artifact that you cannot avoid by yeah, this is implemented in the thermostat.
This is convincing.
Yeah, thank you.
Okay. Okay, great. So I have one more question. So here in your profile, we see here a clear linear trend, but then we see this non-linear temperature profile, which is a standard to simplify just using the Kapitz expression. So I characterize a delta T, and the heat flux is proportional to this delta T. Of course, this is phenomenological, but do you think this is, so the Kapitz understanding of this effect is capturing the true physics that is going on here? I mean, in terms of the constitutive equations that would relate the heat flux at the temperature profile, do you think that we need something beyond Capizza to fully describe this, or you think that we should only rely on MD and forget about?
I mean, it depends on what your purpose is, because here we had some sort of specific purpose chasing for technological applications and a very simple description which assumed that an infinitely sharp surface interface and temperature drop would have worked. Of course, if you are interested in the interface properties of the material to a more refined extent, you should consider the interface as a physical system itself. You should really try to look what is going on there, consider the interface thickness, consider the interface as a region where the thermal conductivity is is way higher than the two materials, and this has to do with the particular interactions between the two of them. But it really depends on the specific interest you have. Plus, I think that you should rely on more refined technique, because if you want to model the interface as a physical system on its own, you really need to take electrons as well into account. As you perfectly know, a diode is just a p-n junction, and you get a definite, I'm doing the comparison because whenever you talk about the electrons, this pops to my mind. You know that just the difference in doping creates a voltage drop. So if you don't describe the electrons, you cannot claim that you are understanding the full picture when it comes to the physics of the interface. So this is fair and works as long as we are interested in these bulk-like properties.
Okay, and one very, very last question related to this. So you mentioned at the end that you might extend your work by considering machine learning potentials.
Yeah.
So your goal or your motivation is basically to train it with DFT, so to capture some electron effects, electron screening effects, or it's more about... So I understand that when you say machine learning, you mean training it with DFT.
Yeah, but I would say that is just to describe better to better figure out what the true interaction between the ions is, because regardless of how well you model the interaction between the ions, you are completely neglecting electrons physics. And the electrons are completely unpredictable. They are fully quantum at our temperature, whereas nuclei, they are classical particles. Phonons are classicals at this temperature and in these regimes. Electrons are not, and the electrons are completely unpredictable. You know that there are strange metals, there are Mott insulators. We don't have yet the full picture, not even talking about semiconductor, insulator, or metal. We cannot tell, because the Fermi sphere, strictly speaking, is defined only for a non-interacting electron system. As soon as you switch the interactions on, you cannot say, yeah, I still have a Fermi sphere. No, you don't. Strictly speaking, you don't. So you cannot say, yeah, I fill up the Fermi sphere. You know what? You don't have any. So electrons are, that's quantum mechanics. You know better than me.
Oh, excellent. Thank you.
Thank you.
Okay, thanks a lot for everything. I'd like to start first by congratulating, in the name of Claudia and Alberto as well, congratulating you and Ricardo for putting up this nice work and a very nice presentation, I have to say. I quite enjoyed reading your thesis. In particular, I quite like a couple of ideas that you proposed and developed within chapter 2 and 3. I'll go to this in a minute. This is a positive thing. As a negative thing, perhaps the only thing that I missed a little, I'm experimental, as you already may know, this is probably a problem at some regards, is perhaps a little more comparison to things that are already out there from experiments.
Yeah.
We can discuss this a little more in the next couple of questions, but it's true that within chapter 2, there's few work done, as you were very well mentioned in the thesis. Nevertheless, in the part of coherent phonon transport in superlattices, there is some stuff by very recognized guys like the Gang Cheng, MIT, Hopkins in Virginia, and the third group is related to Cahill and basically in oxide superlattice. Anyway, as I said, I find the ideas mostly that you worked in and developed super interesting, and for that, congratulations. So if you don't mind, I'll start by chapter 3.
For sure.
The first thing I'd like to say is a positive comment, and I really like the quantification that you do of the different effects that you have in an interface when you're doing thermal transport. As you may know, this is a field, it's a topic that's regaining a lot of attention. Actually, there's, I think, a Nature from last week published exactly in this kind of things. So there's people who are really interested in this for very obvious reasons, like heat dissipation in electronics and things that you already mentioned. One general question I would make you is, like, you actually chose a very interesting interface, which is germanium gallium arsenide. Yeah. As you very well explained, the lattice mismatch is basically zero. It's 0.5% or something like that. And there's also two key very interesting things there, and that is the acoustic mismatch is very, very small between the two materials, and also the thermal conductivities are very similar. Yeah. So usually you have very good phonon transport at the interface. No, so actually you picked a nice interface. Yeah. Let me put it that in terms of having a high thermal conductor. So my question is, what would you expect in general? This is a general question, okay? It's just an opinion I'm interested to hear, if possible, for interfaces which are a little more aggressive in terms of acoustic mismatch or thermal conductivity mismatch. Not discussing now geometrical aspects, but mostly the intrinsic parameters. We expect similar results, very different. Could this be done, or can this brings problems regarding the calculations, this kind of thing?
So I would say that, first of all, you need for sure to make sure that the system forms. So the similarity in the thermal conductivity and of the two materials is rather necessary, I would say, to have a junction which actually exists in the experiments. You cannot just, I mean, okay, you can have a cold welding if you were in perfect vacuum, probably take any two materials whatsoever, put them close enough, and maybe they will just weld together. But this cannot happen here in real life, on this planet, okay, in this, what is it, atmospheric condition. You cannot, this is the junction where that happens. I would expect that if you take a couple of materials exhibiting a different acoustic impedance, for example, according to the acoustic mixed match model, you would observe in principle a higher, a more enhanced thermal boundary resistance. And this is just pretty general. I mean, I think this could work in a very general way of speaking. I would also think that if you take materials with a very different thermal conductivity, if you can still obtain a junction forming in atmospheric condition, let's say, you would observe a higher rectification coefficient, but the system would be way less stable. So it would be probably even more difficult to then observe rectification in the experiments and stuff. I'm not sure if I answered, maybe I forgot something.
Absolutely, thank you.
Thank you.
Yeah. Then, for example, you show that actually right there, that the thermal boundary resistance between germanium and gallium arsenide actually increases when you study smaller scales. Yeah. Why?
Okay, there are several reasons. The prominent one is that you are not describing the continuum, so the infinite size system, meaning that the number of phonon modes that you have for the left side and the right side, this is a simplified picture still, but the number of phonon modes that you have for the left side and right side of the junction, so for the two materials, does not mimic fully the number of phonon modes that you have for an infinite system. So you will have a more pronounced difference in the two phonon spectra, which implies less compatibility between the two. So every phonon which hits on the interface has a lesser chance to actually find available phonon state on the other side, so it cannot go there. This is why you observe a higher thermal boundary resistance. More phonons get scattered back.
Yeah,
they cannot pass.
Actually, one thing I was thinking when you were showing this is the scales where you see an increase in the thermal boundary resistance are typically well below 100 nanometers or something like this. And this is exactly the regime where in both materials, germanium and gallium arsenide, you expect to have non-Fourier heat transport. Yeah. Meaning, in other words, that you are well within the quasi-ballistic transport regime, which in other words is out of equilibrium, right? So my question is, do you think that this could be, in other words, the explanation for the increase that you see. And that is that you have, of course, a TBR, which is dependent on the equilibrium conditions that you actually have, which in this case is determined by the thickness of the layers that you have, which of course is a competition between the thickness and the phonon free path. This is obvious, no?
Yeah, I think it also. I mean, I haven't thought, to be honest, I haven't thought much about this when I was studying the system, but I would say yes. I would say yes, because in fact, when you are close to the ballistic regime, you would have that, you would really observe just side A at one temperature, side B at another temperature. So of course, the temperature drop at the interface would basically be the temperature drop that you would have at the thermostatic zone. So yeah, of course, I haven't thought about it yet.
Possibly, because I guess this probably you can even comment better, Albert, but the evolution of the out of equilibrium transport equation, of course, will not be the same in both materials. Of course. We have slight differences, and this perhaps, if I'm not mistaken,
I hadn't thought about it, but yes, I would say yeah.
Then do you have any, you mentioned this already, but do you have any, at least with your, let's say, educated guess on why do you find 1/T dependence of the interface resistance? I know it's a difficult question, I'm sorry for that, but it's only out of interest, okay? Instead of 1/3, or you wrote something in the thesis, I remember, that possibly, and you mentioned this, is quantum mechanical or this and that, but any, with your fingers, explanation you have or no? Just by personal interest. I know it's a difficult question.
Yeah, this is a very good question, actually. I would like to have the answer.
Not easy.
I mean, I would say that probably, I mean, here I can just try to provide you with a general picture. When you are using molecular dynamics, you are including phonon processes at all levels. Whereas in the acoustic mixed match model, you're not considering interactions between the phonons at all. That's basically the BI. So there are free phonons, non-interacting phonons. So probably phonons interactions kick in. They should kick in. Indeed, you know that without the phonons interactions and impurity scattering, you would observe an infinite thermal conductivity for every material. So in order to observe a finite thermal conductivity, you need interactions. Here you are taking interaction at every order into account. So maybe something about 3 and 4 order phonon processes becoming more and more enhanced at higher temperature provide us with a better compatibility between the two spectra. So it's easier for the phonons to pass from one side to the other, and that's why we don't observe such a sharp drop. This is, but it's just, this is a very difficult answer. I mean,
thank you. No, it's more than enough. Then in line with this, you show that when the mixing length between the, if I can call it that way, between the two materials increases, you get a larger TBR, right?
Yeah, of course.
Why is that?
Yeah, so you have, pardon?
This is related to this, let's say, the onset of alloy scattering. Is it something related to that or not? Because for me, it's not. I mean, there are a couple of works by Natalio Mingo and Jesus Carrete, like 7-8 years old, where they basically do this sort of tuning, thermal tuning between in nitrides, I think this is, by doing a graded composition change. So this in some, let me say it like in a very simple picture, this helps heat to be transferred from one side to the other one. So I was just thinking, this is disorder, I understand it's different, but do you see why this happens actually? Why when you increase the thickness, things get actually worse?
Well, here I would say that is largely due to the random nature of the process we adopted. Because in my opinion, still my opinion, I haven't simulated this, but if you could make a sort of non-random transition between gallium arsenide and germanium, but just a sort of regular transition, you would not observe anything like that. You would observe something way richer. Whereas here, the fact is that you are basically expanding the interface region, so where the conduction is way lower than the thermal conductivity is way lower than the thermal conductivity of the two materials. So this is just a linear proportionality law. The longer the region where the thermal conductivity is low. Let's imagine that you have a definite very low thermal conductivity in the mixed zone. If you double the length of the mixing zone, you will double the contribution to the
So probably
the TBR.
Related also to disorder, to local disorder. I guess.
I would say yes. I would rather claim that this has to do with disorder rather than any other artifact or physical phenomena.
Okay, then one more from this chapter, and then I switch to the next one, and that would be you showed also something that is super interesting to me for me to observe, which is that you do not see a dependence on the interface conductance with roughness, which for me is surprising and interesting. My question is, would you expect that for two materials with very different acoustic, thermal properties, whatever, this would be the same case? Is this a material independent property observation, in your opinion?
I would say that, of course, you would observe a different scenario compared to our, from the one we have found. We would have wanted, let's say, to see what happens if you take different materials, but rather than different materials, we expected that we would have found some specific trend, because if I don't remember the exact paper, but it has been observed in the experiment as well, that with increased root mean square, you observe a rather linear, I'm thinking about the plot, okay, a rather linear increase in the thermal boundary resistance of the heterojunction. We sort of imputed the complete absence of any clear trend in our simulations to the finite size of the computational cross section, and we also thought, like stemming from the convergence results at the beginning, that if we repeated the simulations with the cross sections that were available to us, still the results would have changed much. Plus, you have to think that when you are increasing the cross section, the weight of the computation increases quadratically, because the number of atoms involved scales quadratically if you increase the cross section. So we did not even try to assess whether if our assumptions were right. We were like, okay, with this geometry at this scale, you do not observe any trend. But yeah, I would say that with different materials, different acoustic impedances and stuff, could be. Yeah, I would expect that still it would be a very minor thing at this scale, a very minor one at this scale.
So in line with that, and I switch now to chapter 3, if you don't mind. Actually, this is just a comment. No, I mean, one thing that I think would have been very interesting, or could still be very interesting, it would be to correlate these two chapters. Meaning, when I read chapter 3, I was really looking forward to see details on the interfaces as you did in chapter 2. Because this could definitely help you to understand a little more coherent transport when you know exactly what happens with the interfaces. Because I really think that all the results I provided for germanium gallium arsenide are really, really nice.
Okay.
Yeah. So there, for example, first question would be, do you need to have a perfect superlattice in order to observe coherence? This means surface roughness, intermixing, whatever you have. Because at some point, your answer is very interesting and says if materials are similar in terms we're discussing, possibly no, right? It's the way you see it, or how you see this.
And it's very particular. That is a very interesting fact. It has made me scratch my head for a long time. No answer found, meaning that unfortunately, the largest system that we can simulate are like 100 nanometers in length, and what is this? This is 8, 10 nanometers in cross section, whereas as you can see from this picture, here they have 100 nanometer in diameter. So we are completely at another scale. This influences the simulation in a very large number of ways. So I would say that this is fascinating, because actually when you have the experiments, in the experiments, coherence is observed. There are very famous papers, like very, very famous one, where this transition has been observed in practice, not only in the simulation. So we are super happy with that. But I would, even here, if I'm not wrong, we have grown, not me, but people have grown some perfectly flat interfaces, literally atomically flat interfaces. I would never, I'm sure that you don't have that kind of control over the interface kind and over the possible alternation of different interfaces when you grow superlattices of this size. Here, everything is way less precise and way more random. So here you still observe coherence, and according to what you observe in the experiments, somehow you would say that you should still observe coherence in the last line, in the yellow one, even though theoretically speaking, strictly theoretically speaking, it is okay not to find any coherence, because when you break the periodicity, even if it's a very, very subtle periodicity breaking, it's incredibly subtle, you do not have any k-vector at all. You still have Phonon modes, but since there is no periodicity, you don't have any k-vector. So in principle, you can have an infinitely broad range of very low frequency modes. They are all just collapsing to zero frequency oscillations or very high oscillations. But the modification of the spectrum, here I plotted the Phonon spectra in the continuous limit. Here, if you could resolve for a finite material, you would see it's not a continuous line, just points. Okay, these are specific Phonon frequencies. This structure is a direct and straightforward result of periodicity. Theoretically speaking, pure periodicity. Maybe you can do something treating the periodicity breaking as a perturbation. That is beyond the scope of this thesis, by far.
So then, again, within chapter 3, sorry, I would ask you, what is the reason for which the minimum that you observe in the thermal conductivity as a function of the thickness of the periods does not depend on temperature?
Look, I would say that is not the case. I would say that is not the case. Here I did this. I kept the temperature bias fixed, so the temperature across the nanowire or the superlattice was kept fixed, and we only varied the period. But indeed, if you could modify the temperature, you would modify the mean free path, and then you would observe a modification of the position of the minimum.
But you have this, no? I think you have this in the, which slide is this? I don't remember.
Sorry, maybe
probably, I don't remember which one is it, but you, yeah, exactly, there, bottom left.
Okay. Well, in that case, so when we simulated the bulk, it has to do with an annoying fact, that is that we are simulating a finite length junction.
Yeah.
Since we are simulating a finite length junction, you will have the number of Phonon modes along the direction, the transport direction decreases considerably. And that's why we have to simulate very long periods in order to restore the linear increase in the thermal conductivity as a function of the reciprocal interface density. For the transport equation, for the Boltzmann transport equation, well, maybe it's because in the acoustic mixed match model, maybe it's because the dependency of the TBR, maybe it's because of the reason of the topic we were discussing before. I haven't thought about this, but okay, this is my answer now. It's because here you plug the interface effect, the interfacial effect with your hands, like by hand, and taking it from a phenomenological model. I'm not sure, to be honest, I'm not sure if they actually put a temperature dependent scattering rate for the interfaces when they implemented the code.
Yeah,
because I would really guess that you would observe a shift in the position of the minima. This is physics. This to me is physical intuition.
Yeah. Thank you for that. Then, what time is it? Okay, I will slow down now. One more on this chapter, that just is, again, an opinion, and that would be if you do see any sort of output in terms of possible applications, it's just an opinion, again, okay, for coherent phonon transport or for these kind of things. In other words, people have been discussing this, I would say a little before the superlattices, and this dates all the way down to second sound. We're speaking on the 60s, 50s, something like this, on helium, no? First experiments on solid helium, and then in sodium fluoride, bismuth, and a couple of more guys. Then this idea of inducing coherent transport by doing this
Yeah.
by acoustic matching or whatever appeared. So my question is, do you think this idea of coherent phonon transport is useful for anything, or is just a detail that is interesting for us mostly?
Well, I am a theoretical physicist, so to me it's super interesting. But
To me as well.
yeah, it's super interesting. I think that there are going to be many technological applications, but we will get to them only when the degree of control we have on these physics becomes way higher. Because for the time being, I mean, if you think about it, we have a very good control of light. Basically, not most of our technology, but a great part of our technology relies on the control we have on light, and we can control. Maybe we have phasers, which would be the analogous of a laser, but for sound. But they are not efficient devices yet. We are far away from that, and it's also because we are at the dawn of the nanoscale era. Basically, we are just approaching that in the last decades. So up to less than 20 years ago, no one ever observed coherent phonon transport. So we are just at the beginning of it. So I am pretty confident that within, let's say, 1 decade and a half, we will see technological applications. Even in phonologics, I mean, or maybe even visual. What is that? Because at the very beginning, I provided you with something which probably has the answer inside of it. We have a lot of applications for sound, but our degree of control over the phonons is very poor. Being able to control phonons by means of coherent phonon transport would really pave the way to extend the scope of the applications throughout all of the spectrum. And way farther than this, because I mean, phonons, okay, the phonon picture explodes at some point because you don't have, I mean, you have a finite lattice spacing. So in this condensed matter, phonons can only reach some maximum frequency. But you also have phonons in neutron stars, in nuclear matters, till you have phonons. So now we are very far from that. It's sort of fantasy, but in principle, it's physics. Okay. So yeah, we will. I'm confident. It's hopefully I will see it in my.
You're right. So I'll just wrap up with 2 final questions, related mostly to the fourth chapter. Sorry, and that the first one would be that. I'm not sure if you did think about this, but for me, it would be very interesting to see a correlation between the local minima. I mean, we're mixing material systems, I know, but a correlation between the local minima that you observe in the thermal conductivity in the superlattices with the structure of folded phonons, acoustic folded phonons that you see. So the question would be, I think this would be very interesting to correlate these two. I'm not sure if somebody did this, and I don't know that. But the question is, can you foresee any direct correlation between the number of modes or whatever quantity you would like to associate to the folded acoustic phonons with the minimum that you observe? Or would you think that you could establish some correlation there?
Well, to be honest, I would say no.
Okay.
The reason is not so simple, but up to my understanding, I would say no. And it is because the emergence of the minimum, here I plotted it. So it has to do also with this thing and the existence of a mean free path for the phonon. So if here you could repeat the simulation at different temperature, these would change the mean free path of the phonon, and these would change the position of the minima. Because phonons, if their mean free path becomes shorter and shorter, they would become able to experience the sequence of interfaces, even if the period is smaller and smaller. And the converse is also true. If you can go at lower and lower temperature, you would see that the minimum shifts as well, because phonons would become able to experience a superlattice made of bricks, basically. Whereas if you take bricks and you do like this, you don't see any coherent regimes just because you have primitive cells this large. So I would say that for these reasons, the fact that you observe a minima doesn't really have to do with the number of phonon modes that you have, but rather with the fact that you have a scale. That is the point. It doesn't matter what the superlattice period is, as long as you have, of course, you need phonons which are, you need a superlattice. So you need enough atoms inside the primitive cell to allow a localized perturbation to exist and propagate within it. If you don't, if you just have one species, one red dot and one blue dot, that is a molecule. So you don't have coherent transport in gallium arsenide, for example. You need a superlattice. So you need a primitive cell which is large enough to allow localized phonon modes to exist within the cell and to travel within the cell and experience a sequence of interfaces. But as soon as you have it, you will observe a minima. So as soon as it doesn't really matter, you know perfectly that the number of peaks, well, okay, this is Raman, so there is also the optical thing, but the number of phonon modes really strictly depends only on the number of atoms that you have inside the primitive cell. So you know that you will see at least these many peaks, and then the electrons may switch off. Some of them will not be Raman active. They will be optically irresponsive somehow. But still, you cannot say from these where the position of the minima is. You will know that there is going to be a minima. So there is no direct correlation. I mean, if I look at something like this, I would say, okay, you have enough atoms in the primitive cell. So yeah, you will see a minima in the thermal conductivity. If I look at that, I would say, okay, you have a slight number of atoms inside the primitive cell. You are not going to see a very sharp and pronounced minimum, so because you don't have much room for the complete transition from the coherent to the diffusive regime. But still, I think that if you compute that, you would observe a slight minima. Maybe this is the most pronounced correlation you could expect, in my opinion.
I see it the same way, I think. So the last question is, I think you already answered this, and this is basically if you would expect to see a minimum for the case of the twinning superlattices when you have interaction, of course, and the interfaces, but you somehow already answered this right now, I guess. But if you would like to comment, please.
Yeah, it's basically the same. I mean, you would serve a very, very slight, because in principle, you know, if you can make your simulations and computation or experiments as fine as you wish, as precise as you wish, you will always observe it, because theoretically it's going to be there. But as you can tell, it's rather unlikely to think that a single phonon, you have a localized phonon, which is a very high frequency one, so you really would need to be able to excite a very, very high frequency phonon and make it perfectly localized, and it should be able to travel for 3 atoms. Are we talking about one phonon traveling for 3 atoms? That's close to the threshold. You cannot, then there the phonon concept sort of fades away. So it's delicate. Of course, with longer superlattices, of course, that makes sense.
So with that, I will stop. Thank you for all your comments, answers, opinions, and reviews.